Nightwood has kindly shrunk his, 100 hours of sensitivity and calibration into half. This is called the essence, right, for this, the crucible, or this distillation.
Indeed. Jeff asked me to make some comments on sensitivity analysis and calibration. I'm going to, in reflection on the fact that we'll probably be discussing this material in considerably more depth later this week, I thought I'd keep my comments to a smaller number of essentials. Within the sensitivity analysis area, there's those who have worked here with models will recognize there's a wide variety of types of sensitivity analysis that can be conducted with models. The term is quite overloaded. It can be used to refer to experiments that involve simply varying a parameter, a single parameter at a time, multiple parameters at the same time, specific sets of combinations of parameters, such as using Latin squares or orthogonal arrays, which capture all possible pairs of values, or the guarantee that a given value for a given parameter will occur at least once. And we can also do sensitive analysis with respect to model structure, for example. We'll be touching a little bit more on some of these components later in the week, but what I really wanted to do was to give people a glimpse with respect to AnyLogic of some of the very useful ways that AnyLogic helps facilitate this sort of sensitivity analysis. I do this for two reasons. First of all, the sensitivity analysis is a very important process to undertake in the context of model exploration. It's important sometimes for model validation, such as with extreme value tests. And it's important for highlighting for us particular uncertainties which may have very large effects on outcomes. I'd also do it because it's a distinguishing factor between platforms. So there's some platforms that support it naturally, others for which it's more painful. In case of AnyLogic, it turns out to be well supported for certain basic forms of sensitivity analysis. So what I'm going to do here, for anyone who would like to follow along, I've opened a model called Sar Agent-Based Calibration. You could find it by going to example models, and if you click on the examples right here and scroll down, you'll find Sar Agent-Based Calibration. This will actually, it's a very nice model that originated with XJ Tech, and it helps illustrate some of the support in place for this. When we're dealing with sensitivity analysis for an agent-based model, there's several types of relevance. One very basic issue is we're dealing with stochastics. We're dealing with a situation where a model will typically be yielding results for each time we run it because of variability and when transitions occur, the vagaries of who sends message to whom. For example, variability sometimes in the initial state of the model, etc. AnyLogic provides a type of experiment known as a parameter variation experiment, which helps us investigate stochastic variability as well as varying parameters over time. And if you open up such an experiment as is present in this thing called Monte Carlo 2D histogram here, you'll notice that in the General tab, you can specify what sort of variability do you want to introduce. And one option is to simply run the model with no variability at all. This is an SIR model that's represented. It's a spread of infection. It's a great little teaching example. And as we saw before, individual starts infected, spreads it to others. In this case, I believe neighbors, and we have a spread of infection throughout the population. So I'm running this this example, and you'll see something different than you've seen before. Specifically, there'll be a type of chart here which is doing something quite distinctive compared to the examples we've previously seen. Specifically, in previous examples, we had a trajectory run over time for a given scenario. We would run that scenario and see a trajectory. If we ran again, we would see a slightly different trajectory. Here we see a visualization. In form of a 2D histogram chart, which expresses the variability across multiple given realizations of this model. So with a fixed set of parameters, we're actually not varying the parameters here. We're running the model times, and this is summarizing for us the results of these many realizations. You'll notice, because I'm running this on a dual core machine, that you have the different cores running simultaneously, so that they're processing different realizations at the same time. It's embarrassingly parallel, as we talk about in computer science. And you'll see through the various runs that there's kind of a predominant sort of mode, and then there's variability about the mode associated with stochastic variation. This will sometimes be more pronounced, sometimes less pronounced. If we want to interpret that, and I'm going to have to apologize because it's actually in this presentation here, what we'll see is that there's variability about this component, and AnyLogic provides several ways of summarizing this. One is by showing so-called bins, where we mark a given square here, which the occurrence of a dot in a given square will be representative of how many different trajectories fell at this given interval of time, represented by the horizontal sort of component of the square, fell within this level of value. We're showing the number of infected people. And it'll be accumulating numbers of trajectories for each of those little boxes that have fallen in that value. So when we're showing the bins, we're essentially showing a 2D histogram. It's a histogram in the sense we're expressing the number of times we got a certain range of values, but we're doing so in 2 dimensions. Time on the x-axis, and the value, in this case the number of infecteds on the y-axis. And you'll see many trajectories that come down the same way, but there is this certain amount of variability about that. There's another option provided by AnyLogic, which is to show envelopes. So here we're showing envelopes around the median, within which a certain number of values lie, and we can specify what those envelopes are. And in this case, it's kind of like creating a series of box plots. So we'll have the median, we'll have some, say, quantiles around it, or deciles, or empirical fractiles of some sort, according to the bins we specify. And then we'll have sort of whiskers associated with the farthest out points. So these are 2 ways of summarizing the variability that results from many realizations of a model. Now here, to be clear, we haven't actually varied any parameters. We are simply seeing, writ upon this diagram here, an indication of variability across multiple realizations of the same model with the exact same assumptions about parameters. And we see that there is variability. It's actually a bit less visible on your screen than it is on mine here. And sometimes you'll see it quite pronounced. There's a little bit of differences conceptually with the show bins and the envelopes, particularly when you have multimodal data. It'll show up more clearly on the show bins. And it turns out that we can throttle how many runs we do based on statistical considerations on reliability of the estimates of for example, the mean. So AnyLogic provides a way of throttling automatically the number of realizations done to secure a certain level of confidence concerning the envelopes around the median. However, this same type of analysis could be used when we vary parameter values. Again, that's just one sort of sensitivity analysis. But for example, we could vary parameters systematically in a given range. For example, we could change in this model assumptions about the duration of illness, which is going to express how long it takes someone to recover. So this average illness duration. We could end up wanting to, say, investigate different assumptions about this that might cluster about the mean that was proposed. So if what we've proposed normally is the default value is 15, perhaps we want to step these up from 5 to 25, and excuse me, step of 5 and up to 25, and we could then run this. And in this case, it will be doing a 1D sensitivity analysis. It will be varying the value of average illness duration for successive numbers of runs within these ranges. Now, for each of these, we could run a set of replications or run a set of realizations. In this case, we've simply run the model in a single realization, a single run through with a particular random number for 5, for 10, for 15, for 20, for 25. And it's showing sort of the degree of variability induced by that in terms of this output. So here this was a one-way sensitivity analysis. AnyLogic, the same basic mechanisms could provide for a two-way sensitivity analysis. So for example, perhaps we wish to vary the simultaneously the infection probability, and I think originally it was 0.8 if I'm not mistaken, and perhaps I want to vary it from 0.1 up to 1 in steps of 0.1. This would now permit a two-way sensitivity analysis, again summarized in this this Monte Carlo histogram. And you'll notice that there's considerably more variability. Unfortunately, it's kind of bled out on this screen, but there's actually a substantial number of runs that are reaching their peak out here, and even several that are reaching it out here. The predominance reach it back here. Unfortunately, the screen resolution is just not, or screen coloration is not capturing it well. So here we've run 50 runs, so 5 of one and 10 of the other, that are sweeping through these two spaces. So that's an examination of sort of some of the direct grid-based sensitivity that can be performed. However, we could also take a very different approach and, for example, draw values from distributions. So, for example, for a contact rate, we might draw a value from a distribution, perhaps a log normal distribution with some log mean and some log standard deviation, something along those lines. And we could put in an expression here that would express a draw for it, and this would allow then an examination of sort of variability when drawing things from a distribution. So excuse me, it's throwing an error here. So it must not have been happy with something that I just gave. Maybe I gave the wrong number of parameters to it. So what is it unhappy about? There we go. It requires 3 arguments. Okay. Okay. So the third argument is what? The min? Something like that. Andre, do you happen to know? For log normal, I can't remember off the top of my head. I think it may be the min or the max. So here we're now drawing one of the parameters. Instead of sweeping it across some space with a defined number of values, we're now drawing a particular value from a distribution while sweeping the other one over space. My point here is one could perform the sensitivity analysis either in a regular sweep or by drawing values from distributions. And each of them will sometimes confer value. Drawing from distributions, because of the unfavorable scaling of numerical quadrature, if you're varying a large number of parameters, the number of points in a grid will explode geometrically with the number of dimensions of that grid, whereas it may actually be much more efficient if you're varying a large number of parameters to draw each from a distribution, a sort of Monte Carlo sort of way. So we have the option of doing that within AnyLogic, or of simply making use of grid-based sensitivity. So these are examples of types of sensitivity that can be conducted with AnyLogic's built-in sensitivity analysis, and each has some theoretical foundation associated with them. Any questions about this? Yes. Very good. Yes, right. Sure. Sure. Yes. Okay. So help me understand your situation a bit more. I'm understanding it in two possible ways. So, yes. 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 It's a survival curve over time. So you have some hazard rate over time, for example. Okay. Yes. Yes. For the viable distribution. Yeah. Yes. 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 Right. Okay. Okay. Yes, yes, I appreciate what you're saying. So what you're hoping to do is to draw from the joint distribution, essentially. Draw values from the joint distribution. And I think what you're noting is that here we could draw values from particular distributions, but how is it that you would capture that sort of joint variability? Okay, so that's a good question. I could think of ways that I could do it appropriately. For example, I could quite readily have a parameter here which actually passes in a pair of numbers. Let's suppose it's a bivariate sort of thing. Passes in a pair of numbers, and I actually draw from a so I have a function which draws from that distribution and passes that in, and then the sensitivity analysis is essentially used to just sort of automate it and put it up on this component here. I would still need some code to draw from the joint distribution, and probably what I do in that case is have a marginal and then a conditional. So I draw from one, and then I'd have a conditional distribution, the other conditional on that, and draw that value sort of in a Gibbs sampler sort of way, and then sort of use that accordingly. Well, okay, this is what I was referring to, though. I don't believe, and I should have made it more explicit in my answer. I don't believe that you could here write an expression for contact rate that depends on average illness duration. I may be wrong. Maybe you could. Maybe AnyLogic. It depends how this compiles to Java code. Whether you could write an expression here conditional on that. And off the top of my head, I'd have to go sort of take a look at the code and see. My guess is that AnyLogic would complain. Let's what the heck. So if I were to make this guy have a, let's just put something uniform from 0 to average illness duration. I mean, this is meaningless, right? In this case, because the units are completely different. But I'm just trying to see, in principle, could you do this? I suspect AnyLogic will be displeased with my build completed successfully. Okay. Do you feel lucky? So Okay, well, that's not totally surprising that you get so many zeros, but it does appear. Now, I'd want to go take a look at the code output from this to see if this is actually meaningful. But I believe there's good reason to believe that, in fact, you could have conditional distributions here. You could have the marginal here. So you draw this from a normal. You draw this one from a gamma, which is conditional on this normal for one of its parameters, and it appears that that would work. I was thinking of a more complex scheme. If that didn't work, you could still do it by having an external function that draws from the joint, returns a pair of values, and then you pass that as a parameter. I mean, let's recognize here that parameters in AnyLogic aren't limited to primitive types. I mean, we commonly see them as doubles and ints and so on, and that's because they're very useful. But we can actually pass in objects as parameters, for example, and the object could be a pair of double, which gives values. So this is one of the great things about AnyLogic's design, is that the use of parameters permits quite sophisticated things like passing in closures, passing in essentially objects, which implements an interface that you could then call as a parameter to main. And I realize my comments here are speaking only to a small subset of the audience, but that's the type of flexibility you might want to take advantage of. And here you can actually have conditional probability distribution. So that's how I do it. Does that make sense?
Yeah, sure. I have it set up. I do my y value normal Excel.
Yeah. That sounds like a painful process, gentlemen. I think unnecessarily painful. I think you could do it fruitfully in here. The question is, often we can decompose a multivariate distribution into a successive series of, using a simple classic conditional probability distribution. We can decompose it into a set of successive draws from familiar built-in distribution. Okay. So great question. Any other question on that? So sensitivity analysis like this is quite useful. It's a routine part of modeling practice. And one thing I should emphasize in this area as well as other areas of AnyLogic, it's very, very helpful to recognize that these constructs that you're seeing here, such as these displays, you're not slavishly bound to them. You can, for example, stop this, and it'll finish its run here. But I could actually go down and drill down and find the actual data that's being accumulated here. Okay, it's actually still going here. But fundamentally, I should be able to go here and do copy all, and then I can go over to my handy Excel, and I can paste in sort of the values on which this 2D histogram is based. Okay, and these will show for successive time periods, shown here on the x-axis, and for particular values, the number of trajectories that fell within that range. And you also have to be careful because it takes into account the number of realizations run and so on, but in accumulating these values. But in short, these are useful constructs. This is very much in line with what I understand to be sort of AnyLogic's philosophy. You're provided with a set of constructs to make things very easy, but you always have recourse to break things down. You typically have recourse to break things down, drill down, and then take the data, export it elsewhere, do further analysis. So I might dump data into R or something and do further processing of it. Prefer R's 2D histogram output or what have you. Okay, so comments? Okay, so that was just a glimpse of some of the mechanisms involved in sensitivity analysis. I want to illustrate some mechanisms for calibration. It would be my thought by Jeff's request. And we could touch on this much more later in the week. Questions? Okay, so I'll go on to calibration. And again, forgive my brutal brevity. perhaps that wasn't the word that came to your mind, but okay, so here we'll talk about calibration. Calibration is just one way with dealing with what I call data gradients. We often do things called backing out, which is to sort of analytically derive an answer, but fundamentally we're trying to calibrate here from diverse data sources, as I've noted, and we're basically finding sets of points in a multidimensional parameter space. Sometimes this space may include dozens of dimensions even, where the emergent behavior of the model best matches what data we have, from the external world. Fundamentally what we're going to do is to do an optimization on this space. We'll walk over the space for different values in an intelligent fashion using a global optimization algorithm, which is quite sophisticated. I believe under the surface it's based on sort of genetic algorithm type characterization, quite a bit more sophisticated than what you'll find at Benson, for example, with sort of Powell optimization and hill climbing. And you go over this space in an intelligent fashion, trying to find points in space that offer the best fit of the data. Or to put it another way, they minimize the discrepancy between what the model produces on the one hand and what your evidence from the world tells you. So it allows us often to leverage large amounts of diffuse information we have about overall system behavior, no one part of which allows us to estimate a parameter. Often this optimization algorithm will run the model many, perhaps thousands or more of times to find the best match. And it turns out there's a whole theory of how to best match this sort of data. We're going to use this same model to try to do an effective matching. So we're instead, in this model, for those who are following along with AnyLogic, we're going to go to the calibration experiment here. So we have been working with the parameter variation experiment called Monte Carlo 2D histogram, which is the description for the type of data set we use to accumulate that 2D histogram chart we saw. We're going to be going here now to calibration. And this is a different ball of wax. We're going to here be adjusting parameter values and judging their suitability. And you'll find a bunch of pieces of this specified. So you'll notice here that we can specify either in a fixed fashion the number of so-called iterations to do. In other words, the number of steps in which we will successively search for that sort of optimal place where our parameters yield outcomes, yield results over time that best match historic data. In this case, it'll say we're looking at 500 different stones, finding the stone that offers the best results. So essentially, we may be starting up at the top of a mountain, which represents a large error from the empirical data, and we're trying to find our way down to find that set of parameters that yield the best outcomes. And we may get stuck here and then we'll fall down to the floor, and that's the lowest we can get. We're going to identify how many steps we're going to go, or we allow it to automatically stop based on some criteria. We're going to allow it to vary certain parameters, so it has a certain latitude in terms of how wide this space is. We'll examine a certain number of beta values. We'll allow it to explore a certain number of mu values. For example, maybe one's a probability and logically has to be between 0 and 1. And then we'll further specify a function which specifies the discrepancy involved. In this case, we're using a built-in AnyLogic function called difference, which takes the difference between some data accumulated from the model, output from the model, and corresponding data that we have available from the world. So it's almost like we have some data available from the world, and then each time we run the model, we'll accumulate some data that corresponds to that external data from the world. So maybe we have external data from the world on number of admissions to a given, to our hospitals within a given health region for H1N1 infections within the past week. And then, so for week 0, week 1, week 2, week 3, we have some historic data. And then we're going to accumulate corresponding data from our model. and then we'll compare the two. And this difference function is going to take a sum of squares differences between them, and that's built into AnyLogic as of AnyLogic 6 something odd. So there's a built-in function taking so-called Euclidean distance, so square root of the sum of squares. Okay, so we can also define a custom difference matrix if we're so inclined. We might encode historic data, for example, using AnyLogic provides these things called table functions, which those from system dynamics background will be familiar with. And these basically describe, for each successive point in time, historic values associated with it. And you might have one historic table function for, say, for number of admissions to the hospital, another for number of patients currently in wards with diagnosed H1N1 infection, another one for deaths. And these would be functions over time specifying the number of cases. And it allows us to do interpolation, so we can specify what interpolation to use. If we ask for a value, say at 5, how does it interpolate? Does it use spline interpolation or linear, or does it just use the last value? And how to handle out-of-range requests, which is kind of nice. I'm not going to go into this right now, but suffice it to say, we'll go into this later in the week for those who are interested, but suffice it to say that we store this data around so that we could then compare it with the data we accumulate from the model. And for each run of the model, we're going to suck the data out of it that we're going to use to compare. So we'll run the model, and we'll have data from each successive time point that we've accumulated in a data set, which is a mechanism that AnyLogic provides for accumulating data during the model run. We'll take that data set out, and then that's the thing we compare to the historic data. Okay? So this is running, just like a sensitivity analysis, a calibration experiment is running the model many, many times. There's a main that comes into existence, runs this out, and then data gets sucked out of it to become this data from the model. It's compared, and then that main gets thrown away, and we run the model again, and we run the model again. And each of those models we may actually run many times, because if we're doing calibration in a stochastic system, as we are here, with the stochastic model, rather than, say, a deterministic system dynamics model, where we have an agent-based model, a discrete event model, we may run it for a particular set of parameter values, a particular point in this so-called parameter space, and it may yield different results every time. So we may want to do this comparison that we're doing here multiple times. And AnyLogic provides a very seamless way of doing that, which is quite nice, but I won't have time to go into. So I'm just going to, without going into this, I'm going to run a little demo of this, and I can't take credit for this. The credit goes all to those people in St. Petersburg who are working long hours to provide this. But this is a very nice little example that shows some historic data. And I'll start it again so you can kind of catch the first little part. Down in the lower right, you'll see this historic data that we're trying to fit. And up here, right next to it, you'll find various attempted fits of it associated each with different parameter values. And it will be showing the goodness of fit up here in calibration progress. And at first it will be quite bad, but it will learn. It will learn from its experience using this genetic algorithm. So here's the first guess. It's trying various guesses. This is the best one it's gotten. And for each of them, it's actually running a set of realizations. And this is the best one it's found yet. You see it started up here in terms of goodness of fit. It was way off. And then it started to come down. And you'll notice not every run is particularly good, but in general it's getting better and better and closer. And we could run this thing for hours, and it will get closer and closer in its match to this underlying historic data. Now, it turns out there's all sorts of caveats with this. There may be multiple combinations of parameters that match it, for example. It may not be able to match particularly well both this and another time series that you have, and you want to investigate why. But this is an indication of the sorts of mechanisms AnyLogic provides very powerfully to help enable the calibration process, even in the presence of stochastics. Just to sort of comment on that, you'll notice that there's a thing called replications here, and replications is AnyLogic's term for sort of realizations, so number of times it runs each of these, and here we can use a fixed number, or we can vary it to achieve a certain degree of confidence concerning the reliability of the results, and there's some statistics behind this. So in short, AnyLogic allows you to have a stochastic model to try to match it to historic data, not just one time series, but many, many time series, and provides ways of sort of a whole harness to put it into so that it will arrive at good parameter values. And its algorithm for doing this is pretty sophisticated. The algorithm for the underlying OptQuest optimization is a pretty savvy algorithm for arriving at these parameter values, for learning from its best experiences before and combining the insights from several best previous guesses. Anyway, this is calibration, and you can experiment with it in this agent-based calibration that you'll find in the example models. Jeff, have I flogged it enough? Questions? Yes. Yeah. Very different.
Obviously, each problem has its own. So, but what's your wisdom about how you go about it? Because there are many things. How you compare, how many things is reasonable to choose. Obviously, you want to fit everything. You want to fit 100 things, but probably you can't do that.
Yeah.
What's your wisdom in going about thinking about calibration?
Yeah. Well, okay. I'll offer a few comments on that, but I consider myself still sort of a learner in this area. I do a lot of calibration, so I can speak from some considerable amount of experience regarding this. But you know, I think it's very much an art at this point, and I find myself spending a lot of time with my students when they work with their calibrations to help them overcome those challenges. And I've actually tried to write down some of my observations there. First of all, calibration, you have to understand, is one approach to the issue. I actually do a lot of work with Markov chain Monte Carlo techniques that seek not to arrive at one point estimate of the best sets of parameters, but instead to arrive at a posterior distribution for those parameters that we can then draw from and arrive at posterior distributions over outputs, or posterior distributions over, you know, incremental benefits of intervention A over intervention B, and those sort of things. And I think that's a very powerful method. Calibration is, however, a very popular technique, and it's one I do use a lot, despite the limitations of point estimates of parameters. But you know, speaking within that, there's a very rich set of issues at hand here, because what's going on is that the more data you bring to bear on it, the more historic data, the more constraints you have, and therefore the less likely you'll end up in a situation which is underdetermined, where you don't have enough information to calibrate the parameters to judge parameter values, and you end up getting many possible combinations of parameter values, which will all reproduce what you've observed. So generally bringing more constraints to it can be helpful. Now, once you've brought them, you got to try to match them, and that's often not easy. My own observation is that I have learned huge amounts from the calibration process. It is painful often. It takes a long period of time, and students don't like it because it exhibits high degree of variability in terms of their thesis completion schedule, and generally students find that an unfavorable characteristic. The point is that that process, if it's taking a long time, you are probably learning something from it. So it is absolutely essential not to view it as just what my wife would call brutal force, where you're just throwing yourself at it and you're just throwing in new parameters to try to give it more flexibility and so on. It's absolutely important to try to learn from it, because if it's having trouble matching, say, different sets of data you have at your disposal, that will probably be telling you something about the model. It'll probably be telling you something about what may be going on, and you'll be losing a grand opportunity to understand the situation better unless you try to understand what trouble it's having. Why is it it can only match this one or that one effectively? What prevents it from trying to match both? Often you can go in and study that, and there's ways of doing that by systematically manually varying the parameters to understand what it is that keeps those in tension. Because if you can understand that, often that will give you insights into how to resolve the problem, but also potentially issues with the model that could be addressed. You can get clarity on collecting more data. You can understand, oh, it's telling us that there's an inconsistency between our, what we're claiming about historical rates and actually observed cases just for this period of time. I got to go back and find out about the data during that time. Maybe there were some mistakes with it. Maybe it's less accurate than data from other years. Maybe there was something different going on. And so it's often at calibration that I have found the biggest opportunities for learning have happened. And often that will lead me to tweak the model, to add a new distinction in the model. Sometimes it will lead me to find out that the data source I'm relying on is not accurate, needs to be corrected, or needs to be replaced by another data set. And so that pain associated with inability to match is complemented on the positive side by the opportunity to learn. And I really believe in this, and I have a set of kind of principles written up for my students in some form, which try to express some of the sort of how you learn from calibration, how you turn it from a mechanical thing where you try to turn a crank and get it to find the best value to an opportunity for great insight. I think, however, though, that you're absolutely right. You don't want to just throw all data at it. We routinely calibrate things with actually dozens of time series, which is a lot, and we expect quite good matches to them. So I have pretty high expectations. However, it is best practice not to give it all data for calibration, to reserve some of it and then see if it predicts that other data. So we do that as well. We also spend quite a bit of time thinking about what parameters we really want to adjust, because there's a curse of dimensionality. Finding one parameter, it's a so-called one-dimensional problem. We're searching for the best value along some particular axis of this parameter. It's often quite a small space. Once you go to 2 dimensions, now you're searching a much larger space. 3 dimensions, now you're searching a very large space. You need 4, 5, 6. You're going to start running into real issues, and you're going to start running into issues where you want one parameter to vary over ranges that depend on another parameter. This gets into the whole sort of conditional calibration, and there's ways of doing that well in AnyLogic and other platforms with sort of relative coefficients that express the ratio of the two or what have you, and calibrating that from 1 and above. But fundamentally, calibration is I find calibration a sort of battle of sorts. It's me trying to learn from it, trying to figure out, but I guess a battle is the wrong word. It's an opportunity for learning, but it's a struggle to try to get it so that it adequately matches across the board data. It is absolutely essential that you use a discrepancy function that has certain characteristics. The one built into AnyLogic is quite good in these regards, but you want to make sure that you use something which is dimensionless so that you can combine a discrepancy in A, which might involve people per unit of time, with a discrepancy B, which is a prevalence, so it's number of people plus C, which is a cost difference. want those to be dimensional, so you often want to normalize by some value. But I'm starting to exude nerdiness at a level that probably is uncomfortable to most people here. So so perhaps I'll save that effulgence of nerdiness till a later time. Yeah. Yeah. Well, yeah, I have some theories about that. I mean, the sort of explosion of number of values would be mitigated if you had large covariance associated. If there's high coupling between the different stocks, what you may have is a quite lower dimensional. I'm going back to my primordial nerdiness. It's like I'm regressing to early undergrad or something. But
it could be that there's only several parameters.
Yeah.
All the rest of the
Yeah, what you will find is even in quite complex models, in agent-based models, you go up from a system dynamics model to say 7 stocks. That's in principle a 7-dimensional state space. So each point in that space is associated with a particular value for each of the stocks, but it's probably only the intrinsic dimension. The intrinsic dimensionality of the state space is actually much smaller. It's probably exploring a manifold in the state space. It's actually a very thin thing, and it may be 7-dimensional principle, but it may be a 2-dimensional manifold. And that's what we see for agent-based models a lot of the time, actually. In principle, there's a huge state space, thousands of dimensions, because you have all these agents, each of which might have 3 stocks, so you might have a 3,000-dimensional state space. But in fact, the actual state space is quite low dimension because there's so much coupling involved between the different states that if you know something about, if you know 5 people in your population are infected, you know a lot about the likelihood that the other people are infected in your SIR model. If you know nobody is infected, a large segment of the population probably tells you quite a lot about the others. And so fundamentally, there's often more regularities there than meets the eye. And looking at the stocks sort of in isolation fools you, because often there's this sort of correlations between things. And that's what makes calibration hard too, because you bump up this, you try to match this one, it's like squeezing a balloon. Squeeze it here, it pops out there. You squeeze it there, it pops out there. And understanding why it pops out in that way is often a key to real insight about what's going on. So calibration is a love and hate sort of thing.
I want to show one slide which relates to
Great.
what we're talking about.
Great, excellent. So we're going through a calibration process back home right now, and for me, it's a thing of joy also, because it's just this really interesting intellectual engagement, and sometimes students get involved, sometimes they.
Might take a break. That's a break. Nathan Mark's interesting project management overlap, and I think putting these two together might create something interesting. So,
With the whole is greater than the sum of the parts. Are you comfortable with this?
Yep. Okay, what I'm going to use it's a system dynamics model. Yeah, that's all right. That doesn't quite fit, that's all right. That's not true. Picks out bits from the literature.
I'm a civil engineer by background, so this model has a very heavily civil engineering basis, but the fact is it's really kind of generic. If we used to try and calibrate a SAR model, it looked at how people's